Good morning. Today we are going to see the single node architecture. In that one, first we will see the hardware components. Choosing the hardware components for the wireless sensor node, obviously the applications has to consider size, cost and energy consumption of the nodes. A basic sensor node comprises 5 main components: controller, memory, sensors and actuators, communication devices, power supply unit. Figure shows the hardware components of sensor node. First one is controller. A controller is used to process all the relevant data capable of executing arbitrary code. The controller is the core of a wireless sensor node. It collects data from the sensors, processes this data, decides when and where to send it, receives data from other sensor nodes and decides on the activator's behavior. It has to execute various programs ranging from time-critical signal processing and communication protocols to application programs. It is the central processing unit of the node. For general purpose processors, applications microcontrollers are used. These are highly empowered and their energy consumption is excessive. These are used in embedded systems. Some of the key characteristics of microcontrollers are particularly suited to embedded systems or further or their flexibility in connecting with other devices like sensors. They are also convenient in that they often have memory built. A specialized case of programmable processors or digital signal processors, they are specifically geared with respect to their architecture and the instruction set for processing large amounts of vectorial data, as is typically the case in signal processing applications. In a wireless sensor node, such a DSP could be used to process data coming from a simple analog wireless communication device to extract a digital data stream. In broadband wireless communication, DSPs are an appropriate and successfully used platform. An FPGA can be programmed in the field to adapt to changing a set of requirements. An ASIC is a specialized processor custom designed for a given application, such as high-speed routers and switches. The typical trade-off here is loss of flexibility in return for a considerably better energy efficiency and performance. On the other hand, where a microcontroller requires software development, ASICs provide the same functionality in hardware, resulting in potentially more costly hardware development. Example, Intel Strong ARM, Texas Instruments MSP 430, Amtel Atmega. Coming to memory, some memory to store programs and intermediate data. Usually different types of memory are used for programs and data. In WSN, there is a need for random access memory to store intermediate sensor readings, packets from other nodes and so on. While RAM is fast, its main disadvantage is that it loses less content if power supply is interrupted. Program code can be stored in read-only memory or more typically in electrically erasable programmable read-only memory or flash memory. Flash memory can also serve as intermediate storage of data in case RAM is insufficient or when the power supply of RAM should be shut down for some time. And sensors and actuators, the actual interface to the physical world, devices that can observe or control physical parameters of the environment. Sensors can be roughly categorized into 3 categories: passive omnidirectional sensors, passive narrow beam sensors, and active sensors. Coming to actuators, actuators are just about as diverse as sensors, yet for the purpose of designing a WSN that converts electrical signals into physical phenomenon. Communication device. Turning nodes into a network requires a device for sending and receiving information over wireless channel. Choice of transmission medium. The communication device used to exchange data between individual nodes. Transceivers. For communication, both transmitter and receiver are required in a sensor node to convert a bit stream coming from a microcontroller and convert them to and from radio waves. The two task combined device is called a transceiver. Transceiver consists of two parts. One is RF front end and the baseband part. The radio frequency front end performs analog signal processing in the actual radio frequency band. The baseband processor performs all signal processing in a digital domain, communicates with the sensor nodes, processor or other digital circuitry. Figure shows the front end. Power amplifier, it accepts unconverted signals from the IF or baseband part and amplifies them for transmission over an antenna. The low noise amplifier LNA, it amplifies incoming signals up to levels suitable for further processing without significantly reducing the signal to noise ratio. Element like load oscillators or voltage controlled oscillators and mixers are used for frequency conversion from RF spectrum to intermediate frequencies or to the baseband. Transceiver task and characteristics. Service to upper layer. A receiver has to offer certain services to the upper layers, most notably to the medium access control layer. Sometimes the service is packet oriented. Sometimes a transceiver only provides a byte interface or even only a bit interface to the microcontroller. Power consumption and energy efficiency. The simplest interpretation of energy efficiency is the energy required to transmit and receive a single bit. Carrier frequency and multiple channels. Transceivers are available for different carrier frequencies. Evidently, it must match application requirements and regulatory restrictions, state change times and energy. A transceiver can operate in different modes, sending or receiving, use different channels, or be in different passive states. Data rates. Carrier frequency and used bandwidth together with the modulation and coding determine the gross data rate. Modulation. The transceivers typically support one or several on-off keying, ASK, FSK or similar modulations. Coding. Some transceivers allow various coding schemes to be selected. Transmission power control. Some transceivers can directly provide control over a transmission power to be used. Some require some external circuitry for the purpose. Noise figure. The noise figure NF of an element is defined as the ratio of signal to noise ratio SNR1 at the input of the element to SNR ratio SNRO at the element's output. Noise figure equal to SNR1 by SNRI by SNRO. It describes the degradation of SNR due to the element's operation and it is typically given in dB. Gain. The gain is the ratio of the output signal power to the input signal power and it is typically given in dB. Amplifiers with high gain are desirable to achieve good energy efficiency. Power efficiency. The efficiency of the radio front end is given as the ratio of the radiated power to the overall power consumed by the front end. For the power amplifier, the efficiency describes the ratio of the output signal's power to the power consumed by the overall power amplifier. Receiver sensitivity. The receiver sensitivity specifies the minimum signal power at the receiver needed to achieve a prescribed EB by N0 or a prescribed bit or packet error rate. Range. The range of a transmitter is clear. The range is considered in absence of interference. It evidently depends on the maximum transmission power on the antenna characteristics. Blocking performance. The blocking performance of a receiver is its achieved bit error rate in the presence of an interferer. Out of band emission. The inverse of adjacent channel suppression is the out of band emission of a transmitter. To limit disturbance of other systems or of the WSN itself in a multi-channel setup, the transmitter should produce as little as possible of transmission power outside of its prescribed bandwidth centered around the carrier frequency. Carrier sense and RSSI. In many medium access control protocols, sensing whether the wireless channel or the carrier is busy is a critical information. The receiver has to be able to provide the information. The signal strength at which an incoming data packet has been received can provide useful information. A receiver has to provide this information in the received signal strength indicator RSSI. Frequency stability. The frequency stability denotes the degree of variation from nominal center frequencies when environmental conditions of oscillators like temperature or pressure change. Voltage range. Transceivers should operate reliably over a range of supply voltages. Otherwise, insufficient voltage stabilization circuitry is required. Power supply unit. The batteries are necessary to provide energy. Sometimes some form of recharging by obtaining energy from the environment is available as well. There are essentially two aspects: storing energy, energy scavenging, storing energy, batteries. Traditional batteries, the power source of a sensor node is a battery, either non-rechargeable, that is primary battery, or if energy scavenging device is present on the node, also that is rechargeable, that is secondary batteries. Capacity, they should have high capacity at a small weight, small volume and low price. The main metric is energy per volume. Capacity under load, they should withstand various usage patterns, as a sensor node can consume quite different levels of power over time and actually draw high current in the certain operation modes. Then self-discharge, efficient recharging, relaxation, DC to DC conversion are the other aspects to be considered. Then energy scavenging. Depending on application, high capacity batteries that last for long times, that is, have only a negligible self-discharge rates and that can efficiently provide small amounts of current. Ideally, a sensor node also has a device for energy scavenging, recharging the battery with energy gathered from the environment. Solar cells are vibration-based power generation or conceivable options. Photovoltaics. Well-known solar cells can be used in power sensor nodes. Temperature gradients, differences in temperature can be directly converted to electrical energy. And vibrations, one almost pervasive form of mechanical energy is vibrations. Then pressure variations, somewhat akin to vibrations. A variation of pressure can also be used as a power source. Flow of air or liquid. Another often used power source is the flow of air or liquid in windmills or turbines. This is the comparison of various energy sources in terms of energy density. Thank you.